All right. We're going to kind of wrap up or finish, kind of put a little capstone on our base 5 conversation. I wanted to talk about two of the most interesting bases, one of which I think is probably the most used base on the planet, even more than base 10, if you can believe that. Wow. And kind of what their kind of functional purpose is. It's cool to see them in action. Bases are more of a thought exercise in a lot of ways. Base 5 isn't practical or useful for anything, but it's intriguing to think about. And these two actually have a purpose, which I think is even more amazing. We're fundamentally changing how we think about mathematics, which is kind of why it's nice to explore. But just as kind of a review of what bases are going on, remember the unit is always going to be that kind of single solitary one. A strip would be a stack of whatever the base is. So if I'm doing base 3, strips are always going to be 3. A mat is going to be a combination. It's going to be 3 times 3, which would be 9 in this instance. And then a strip mat is going to be 3 groups of 3 times 3, which would end up being 27. Hopefully you can see the 3 9s right here. All right. Every human that I know uses base 10 every day as a part of their life. However, most computations being done in this day and age are all done on computer, which use a system called binary. Binary is mathematically referred to as base 2. It's called binary when you're talking about computers. It's the same thing. If you've already done a computer class, I'm sure you've seen reference to this. I know in years past you might have seen there's different activities and bracelets. Typically they come in groups of 8. So when doing computer coding things, base 2 is its own mathematical idea. It's easy because something is either there or not there. It is either a 0 or a 1. You have only 2 numbers in base 2. You get 0s and you get 1s. Those are the 1, 2 things that you have. Once you get to 2 of something, it's time to add to it. It's time to shift it over to the next one. So if I had a unit, that would be 1. That's a terrible unit, by the way, sorry. If I had 2 units, I can't have a 2. That's not one of my options. They would need to become a strip, and that would be 1, 0. These guys would recombine to be 1 strip and then no units left over. Already it looks like we're at 10, right? And I've only got 2 little blocks there. If I had a strip and a unit, that would be 1, 1. If I had a strip and a unit and I added another unit, oh, look, I'm back at 2. Look, now I have 2 strips, and I actually have 2 units left over. So here I've got 4 blocks, 3 blocks, 2 blocks, and 1 block. This would be the base 10 block counting system that I'm alluding to. And yet, it looks a lot like I'm in 20 in base 2 because of how the strips and unit place values are working. So I need to kind of erase this and have a better workspace, because base 2 numbers are going to get huge in a hurry. I like how I immediately just stupidly broke the rules of base 2 and wrote down 20, like that's a thing that happens in base 2. Of course that doesn't happen. Silly me. These 2 strips would also need to be recombined into 1 mat. So this wouldn't be 20, goofball. It would be 1 mat and then 0 strips and 0 units. So it would be 1, 0, 0. That's what makes it stand out, is that once you have 4 blocks, it looks like 100. It is 1, 0, 0 place value. All right. Surprise, someone came in. Okay, so let's get rid of all this nonsense. So I got to be honest, there's only so many blocks I can draw. So in binary, I'm going to start to really refer to the exponential side of things. So let's just give me a binary number. I got 1, 0, 1, 0. That feels like enough for right now. And this is going to be base 2. So I'm going to say, all right, this is how many units I would have. 2 to the 0th power is just 1. This would be 2 to the 1st power. That would be a strip. That would be a 2. This would be how many 2 to the 2nd powers. 2 times 2 is 4. And then this would be 2 to the 3rd power. So again, bases imply you have a strong understanding of exponents, because that is not going to be a 6, right? So units are going to look like this. They're going to be 1s. Strips are going to look like 2s. Mats are going to look like 4s. That's 2 times 2. And strip mats are going to look like ooh, I should really dial in and think about what I'm doing here. They're going to look like 8s, right? Because they're going to be 2 mats stuck on top of each other. I don't have any units in this particular, change color here, in this particular value. I don't have any units, so that's just 0. I have 1 strip, so that's going to be 2. I have 0 mats, so even though each one of them is 4, this is telling me I don't have any mats, so that's also going to be 0. And then I have 1 strip mat, which is actually just 8. And what's nice about base 2 is that once you calculate this part, you don't have to multiply it by anything. It's not like, ooh, I have 3 strips, and if each one of those is 5, that's 15. It's like either you got one or you don't, which is what makes it so fundamentally easy to work with for computers. All right, so that would be 10. 8 plus 2 plus all these zeros is 10. So it looks like 1,010, but we know it's actually base 2. So I would read that as 1010 base 2. And that would be 10 blocks. All right. Let's kind of push the envelope a little bit here. I'm going to erase this. Otherwise, we end up with just kind of the same things. Boring. How about I got 1, 1, 1, 1, 1, 1, 1, 1. I use this as my example. In computer language, that would be a full stack. You usually use 8 units at a time, and they're either 1s or 0s. So we would say, what happens if we have all of them? Just because I want to kind of show off what the numbers would look like. Well, I'd have 1 unit. That's just the 1. I'd have 1 strip. That's just a 2. It'd be a 1 on top of each other, a strip. I'd have 1 mat. Well, that's 4. We've seen them. I've drawn them. I'm not going to draw it again. I have 1 strip mat. That's 8. I would have 1 mat. So if a mat looks like that, a mat would be 4 of them. 4 mats. Well, 4 4s is 16. Oh, I see something happening here with the numbers. That's just this guy right here. I would have 1 strip mat. So that would be if I made a double of those. It would be twice as tall. My arrow there doesn't really line up very well. Sorry about that. I have 1 mat. A mat of mats. If this is a mat, I would need a mat of those. I'd need 4 of those. Or 2 strip mats next to each other. And I would be 1 strip mat. It's twice as big. Who even knows? And I could go through and I could add all of these up and figure out what my total combination computation is going to be. I'm going to cheat a little bit and just tell you that already that it is 255. And the reason why I know that is because if I added 1, it would domino over and it would increase and change all of these values. And so I know that 1 more than this would just be 1, and all of the rest of the values would have to be changed to 0. I added 1 too many zeros in there. Nope, I nailed it. Which is 256, which is 6 to the 9th power. 2 to the 9th power. And so I can kind of just shorten this video and say, I know that this is going to be 256. I would encourage you to rely heavily on this if you need to keep the video open while you solve, so that you can keep track of the 8 place values that I'm going to give you in binary. Okay, base 16, it's called hexadecimal. I'm going to keep this kind of short and sweet because I think there's just something really cool. All of these are super cool, and that's why I wanted to do one final part about these binary things. Binary is the simplest of all possible bases, and base 16 is not the most complex, but it is actually used and used regularly. And what's interesting, it's the only one that we've talked about that's actually more complex than base 10, which again requires a fundamental restructuring of how we talk about numbers. So in base 10, if I think about my unit, and I will do this as quickly as possible if I've already gotten carried away. Like this strip has got 10 little things in it, right? In base 16, the strip is 16 tall, which means that I can take up to 15 units before I regroup. So what happens when I have 10 units and they don't regroup into a strip? Well, I get up to 9, and I need something that represents 10 units, but I can't put 10 there. That's two digits. That doesn't make sense. The whole point is that the first digit is the units and the next digit is strips. So I find that I'm short a way to represent these values. I know that one strip would look like that and then 0 units, but I don't have a way to represent all of these numbers. And so we have to rely on something that aren't numbers. In hexadecimal, once you get to 9, you start using letters. Again, mind-boggling. So let's talk just briefly about what this might look like. So I will write, in this one, we'll just go one way, which is I will write a number. So let's say my first number is E. That's it. That's all I would write down. That's base 16. So E in base 16 is telling me I have not yet achieved 16, so I know it's going to be less than 16, and I can see it here in my far corner. Sorry, I wrote it way up there. That is just 14. That would be the base 10 version of it. All right? So what happens when I write something like 1C? That's a number in base 16, and I'm going to do better about labeling these as in their corresponding bases because there's a lot going on here. Well, I would need to think about what that would look like. I'm going to draw some pictures because you know me. I would have one strip, and the strips are now 16 in value. And C, refer to my notes, is 12. So I would have 12 different units kicking around over here. I'm actually going to count and do a better job of keeping track of these things. Yeah. So how many total things are there? Well, there's 16 in my strip, and there's 12 more in my C, just loose units kicking around. So that becomes 28. 1C base 16 has a value. Hexadecimal, for what it's worth, is used to write colors. Again, this is a computer thing. Typically, they come in sets of 6, and you will see the digits written from 0. 0 is the thing in hexadecimal and in all bases. From 0 to F, and you would have 6 of those letters in combination. So in that kind of color coding thing, to just keep it super simple, 0, 0 base 16 is white, and FF base 16, all Fs would be black. I do believe that's the direction. I know that one's white, one's black. And then all of the colors and numbers in between would be gradations thereof. So I'm going to do one last, I want to talk about why we would use hexadecimal. I'm going to do one last example here, and then I'm done with hex bases. Let's say I have 3A base 16. Didn't write that very neat, but we'll deal with it. 3A would mean 3 strips, and then A is telling me, again, according to my key, that it would be actually 10, but it isn't 10, right? I can't regroup it. It is just 10 little units. So I would need to say, well, I know that that's 10, but this is 16 to the first power, which is 16, but I need to multiply that times 3. So 3A base 10 would be figuring out what all of these values are. 3 16s is going to be 48, plus 10 more would be 58. You can see bases, again, literally grow exponentially. That word gets overused sometimes. And so 58 is a pretty sizable number, and yet hexadecimal, all you need is 3A, no problem. Again, they get large really, really quickly. I gave FF as my example in hexadecimal. If I were to solve it, it would be 1 shy of 16 16s. And so, yeah, it's 255. That's what it goes up to. So 255 little units are just represented by those 2 little numbers. And 100 base 16 is telling me I would have 1 mat in base 16, which would be 16 by 16, which would be 256. So hexadecimal gets large in a hurry. All right, guys, I'm going to turn you loose from here. I hope you had fun exploring bases with me. This is kind of the end of the conversation, but binary and hexadecimal are kind of awesome. So I thought this would be a good place to stop.